Welcome everybody. Thank you so much.
Thank you. It's always great to be here giving one of these public talks. And I know it's out of my control, but I do sincerely apologize for the weather. Sorry that you can't observe after this talk. But hopefully I'll keep you entertained for the next 30 minutes, talking about how we can listen, in inverted commas, to the universe using gravitational waves. So I'll take you far, far back in history first, to start with around 1609, which is when the first telescope was invented. And then a few short months after that, Galileo used his telescope to point at the sky and see what the sky has to tell us. And one of the very first things that he found when using one of these telescopes is the Galilean moons. So the moons that are orbiting around Jupiter, and that show us that actually the Earth is not at the center of the universe. So this challenging this geocentric model of our universe. So seeing that there are other objects that can orbit around other individual objects in the universe. And this is kind of a very typical example of how we can go out using our instruments, point at the sky, see what information the sky has to tell us, and then interpret that information and understand the laws of the universe. And since then, we've improved upon our telescopes, and we've built bigger and stronger telescopes, and we've sent them even in the sky because we understood that actually we are very limited by the atmosphere of our Earth. And now we point out, for example, the Hubble Space Telescope, which we sent up in around the 90s, and we can, for example, pointing out to a seemingly dark patch of sky, we uncovered thousands and thousands of galaxies, and we started learning more about the properties of these galaxies. And taking you forward to the present day, the James Webb Space Telescope, which I'm sure a lot of you have heard about, is revolutionizing our understanding of the universe using the same principle of pointing out at the sky, looking at what the sky has to tell us, and then interpreting and understanding the underlying physical laws that are giving the observations that we're seeing. So for example, here is one of the beautiful images of the Carina Nebula that was obtained by the James Webb Space Telescope. So essentially what I've shown you is how we observe the universe using the electromagnetic spectrum. So the electromagnetic spectrum is essentially describing these electromagnetic waves, we call them, and these waves come in different flavors. This flavor is dependent on the energy or the frequency of the wave. So the higher the energy, the higher the frequency of the wave, and the shorter the wavelength. For example, gamma rays or X-rays, which are super energetic. And on the other end of the spectrum, we've got radio waves, which have super long wavelengths, low energies, and low frequencies. And across this range, then there's visible light, which is kind of somewhere in the middle, not quite the middle. And we can use this electromagnetic spectrum to do different things. So for example, using X-rays, we can probe our bones because X-rays pass through our skin, but then they're blocked by bones. Or using radio, we can use this for telecommunications. And the electromagnetic spectrum has been deeply studied and is great, is super useful. And what I'm showing here in this figure that I got from NASA is only 3 of the many, many, many telescopes that we have that use this electromagnetic spectrum to study the universe. So, for example, the James Webb Space Telescope probes what we call the infrared. So that's the same kind of electromagnetic wave that you use when you control your television using your remote. So this infrared has slightly lower energies than the visible spectrum. And this is why it's super useful to study the very early universe. It's because the light that has left the objects in the early universe has lost some energy on its way to us and has stretched the wavelengths, and then we receive them in infrared and we see them using JWST. The Hubble Space Telescope then probes slightly higher energies, so it's more sensitive to the visible light. But what's the problem with electromagnetic waves if they're so useful? Well, the problem is that light can be tricky. Light can be absorbed or scattered by, for example, dust that lies in between us and an object that we're observing. And we can somehow try and get around this, so dust absorbs more in certain parts of the electromagnetic spectrum other than the others. So we can be a bit clever and use these techniques, but it's still a big problem. And another big problem is that some regions just don't give off light, or that light is just inaccessible to us because of some laws of physics. So an example of this is black holes. Literally, by definition, light cannot escape these black holes, so it wouldn't be able to reach us. Or, for example, the very, very early universe, when the universe was opaque to electromagnetic radiation, so electromagnetic radiation could just never escape to reach us. And, well, if only, right, there was another way to probe the universe, and I think from the title you probably understood that there is. And it all comes back to this guy that you probably recognize. So Einstein, around 100 years ago now, came up with this theory of general relativity that completely revolutionized our understanding of how gravity works. So before, gravity was thought of as this force. So Newton sitting under his apple tree, right, and an apple fell. So the idea that two objects that have mass generate this force that is attractive. And that is all very true in an approximation. But what Einstein did is he gave us a more sophisticated theory that explained the way that gravity works by explaining this fabric of space-time, which we call a manifold. But essentially what you can think of it is that this space-time is a fabric, and then every object that has mass is an object lying on this fabric. And what do you expect to happen? You expect this fabric to curve. We call this the curvature of space-time. And because of this curvature, other objects in the vicinity can feel this curvature of the object that is generating it and experiences this force of gravity. So actually, John Wheeler put this really nicely, and he said that space-time tells matter how to move because it creates this curvature, but then space-time tells matter how to move because it feels this curvature, but matter tells space-time how to curve. And this essentially is all you need to understand about the theory of general relativity tonight. But this theory has some deep implications and has resulted in a lot of predictions. So one of these predictions is the existence of black holes. So an object that has mass creates curvature, like, for example, our sun, right, which is at the top there. Now, if you take an even denser object, so an object that contains a lot of mass but is contained in a small volume, that creates even larger curvature. This is a prediction by Einstein's theory. So if you take a white dwarf that is a lot more compact than our sun, then it creates this bigger dip. If you take it a step further, so for example, a neutron star, which, if I remember my facts correctly, has around the same mass of our sun, but contained in the size of around the city. So you can just imagine how dense this object is. It goes even further. What happens if you take it even further? Well, you can create this infinite curvature. This is what a black hole theoretically is. So a black hole creates such a dip in the fabric of space-time that it is so strong that not even light can escape its pull. And this was a theoretical prediction, and now we've made observations that have provided very, very strong evidence in favor of the existence of these black holes. But another prediction that came from Einstein's theory of general relativity is the existence of gravitational waves. And Einstein predicted that anything that has mass and accelerates through space creates these ripples in the fabric of space-time itself. So if I move my hand, I've accelerated, I have mass, I just created a ripple in the fabric of space-time. With a catch though, that was tiny, tiny, tiny. So we need really, really massive objects to create ripples that are significant in any way. And he made a lot of predictions about how these gravitational waves should behave, but the main point is that they should travel at the speed of light, that when they are created somewhere far away from Earth and they travel to Earth, they lose energy, and so their amplitude becomes smaller and smaller, so they become very, very small by the time that they reach Earth, and that they stretch and squeeze the fabric of space-time. So the fabric of space-time that lies in between objects. Okay, so there was this prediction, but what can generate sources of strong gravitational waves that we can potentially detect? Well, the first class is what we call compact binary inspirals. So the word compact means objects that are very compact. So for example, black holes and neutron stars. So objects that are very, very heavy and contained in a small volume in space. Binary means that there's two objects that are going around each other, so they're bound together by gravity and they're inspiraling. So inspiraling means that they're falling always further into each other as they go around each other. So for example, a typical example of this is two black holes going around each other. Or you can have two neutron stars. These could be really cool because not only do you have the gravitational waves that are emitted, but you can also have a lot of electromagnetic light, as you can imagine, because they're not black like black holes. Or you can have a combination of the two. So one black hole merging with a neutron star. But it's not just those classes that can generate these gravitational waves, but you can also have spinning neutron stars. So spinning neutron stars, or you can call them pulsars, because they have these jets that are being shot out, and as they spin, we see a pulse as that kind of jet sweeps across the Earth. We'll come back to these. This will be very, very important later on. But if these neutron stars have a tiny blip on their surface, so they have a mountain or a hill, so that means it breaks spherical symmetry, then it could be a source of gravitational waves. Or we could also have what we call primordial gravitational waves. The reason why we call them primordial is because they come from the very, very, very early universe. And these could be caused by tiny quantum fluctuations that were present moments right after the Big Bang, so after our universe went through a period of rapid inflation. And we could see potentially these primordial gravitational waves even further than what we call the cosmic microwave background, which is the furthest that we can currently see using electromagnetic waves. But my personal favorite, and I might have a bit of bias here because this is the topic of my PhD, is when we have a supermassive black hole binary. So what's the difference between a black hole and a supermassive black hole? Well, not much really, but except for the fact that supermassive black holes have a mass of around 1 million to even 10 billion times that of our sun, whereas stellar mass black holes have masses that are around 10 or 100 times that of our sun. And these supermassive black holes, these cosmic giants, sit at the centers of galaxies. So even our Milky Way has one, and we've observed it quite a lot. And when two galaxies come together, which is a process that we expect a lot, very frequently, the black holes themselves can also fall into an orbit, and they can lose energy via a variety of physical processes and can eventually get into a regime where they can start emitting gravitational waves and then even merge with each other and become very strong sources of gravitational waves. But the physics that goes on behind these mergers is slightly different than the physics that goes on between two smaller black holes that are orbiting each other because of the presence, for example, of gas. Right, so we've got all of these sources. Great. How are we actually going to detect these minuscule, tiny ripples in the fabric of space-time? It almost sounds like science fiction, right? A lot of people thought that this would be very difficult to obtain. But I will spoil it for you, and I will say that we have observed these gravitational waves using detectors such as LIGO in the United States. And the way that it works is you just build two very, very long arms that are forming an L shape. So each arm here is around 4 kilometers long. And what we're trying to detect is a distance change smaller than the size of a proton. So can you just imagine the sensitivity that we're trying to probe? And the way that we do this is using lasers. So we're trying to detect gravitational waves using electromagnetic light, which is not confusing at all. But so you shoot lasers up and down these arms of your detector. And by seeing how the laser that is going in one direction is interacting with the laser beam that is coming in the other direction, you can see how the light is interacting with each other, and you can measure these changes in the distances. If you observe one arm stretching, and the other arm in the opposite direction squeezing, then you've detected potentially a gravitational wave. And this is the $1,000,000 plot, the observation, the first detection of a gravitational wave. So this is directly from a scientific paper, but I'm going to explain this to you. So what we want to take from the first row is that there's two columns, right? One says Hanford and one says Livingston. That is because we have two detectors. You don't just want to detect this change and this vibration in one detector, but you want to detect it in both of them. But two detectors that are very, very far away from each other. Why? Because you don't want a lorry passing by on the road close to your detector, detect that vibration, and then think that that's a gravitational wave. You want to see it in the two independent detectors. And now we have a whole array of detectors. We also have Virgo, which is in Italy, and also we have Cagra. The second thing that you want to check is whether your measured signal actually matches your predictions from Einstein's theory of general relativity. So now we have very, very sophisticated simulations that we call numerical relativity simulations that can give you the shape that you would expect from a specific system. So if you have two black holes of two specific masses and some other properties, what does the signal look like? And if you've observed one, does it match your predictions? And in this way, not only are we confirming that it's a gravitational wave, but we can also infer what the masses of the two components are. And finally, what does it sound like? That's the sound of two black holes merging with each other. Not exactly, not quite. It's not actually putting out vibrations that are sound waves into the universe, but we can easily, this is the process we call sonification. So the process of taking some data, so this is the frequency that we see over time, and changing that into something else, so sound in this case. And this is exactly the representative sound that we can observe, that we can hear rather. So let me play that again. So that is a characteristic chirp that we call, that what two black holes do when they merge with each other. And what Matt has given me over here is an Euler disk. And I'm going to set this in motion because it takes a very, very long time to actually stop its vibrations. But this Euler disk does a very, very similar sound. Let me try and capture it. Can you hear it? It will take a while, but the frequency here is increasing. And then it suddenly chirped and it stopped. And that's exactly what we hear when we sonify these signals from two merging black holes. Great, and this has obviously won the Nobel Prize in Physics. It's an incredible discovery. It confirmed a lot of aspects of Einstein's theory of general relativity and has now opened up this new field of astronomy, the field of gravitational wave astronomy, where not only are we looking at the universe using electromagnetic waves, but now we're also listening to the universe using these gravitational waves. And these are two independent probes that can be incredibly complementary to help us understand the universe around us. And since this very first detection back in 2015, there have been almost 300 detections of individual gravitational wave events. And a lot of these, well, all of them are mergers between these compact binary inspirals. So that's the class that we have sensitivity for. And some of them are merging neutron stars, some of them merge neutron stars with a black hole, but a lot of them are two merging black holes. And you can see, if you look at on your left, that's the masses of the objects that we're looking at. So we're looking at objects from just a few times that of our sun to around 100 or 200 times the mass of our sun. This is because gravitational waves come in different frequencies, and I'll touch back to this. But when you build a detector, just like when you build a telescope, you're only really sensitive to a particular frequency range. And we built these, we tuned them to listen to these stellar mass black hole mergers. And what I said before, this kind of the way that gravitational waves and electromagnetic light can be really complementary, we have a name for this in astronomy, and we call it multi-messenger astronomy. And an example of this multi-messenger astronomy is if you observe an object with both gravitational waves and with electromagnetic waves, because they're two separate messengers in a way, carrying information from the event to our telescopes and our observatories. And there's a very special case, the case of GW170817. The numbering convention here is related to the date when it was observed. Unfortunately, astronomers aren't very creative sometimes. And what this was, it was a neutron star merger. So two neutron stars merging with each other. So here we do expect there to be electromagnetic radiation that is being given off by this event. After the detection of the gravitational waves, there were over 70 observatories, if I'm getting my facts wrong, across 7 continents and also from space that pointed their telescopes towards the region where we thought this gravitational wave came from, and actually saw this event using a myriad of electromagnetic observations across the different time evolution of the system, which is just incredible. And we learned so much about the physics that goes on in these neutron stars. Unfortunately, we've still been waiting for another event like this, and we're all just crossing our fingers. These events can be rare, but it's also a little bit tricky to localize, to understand where the signal came from, the gravitational wave signal came from the sky, so that then we can actually go and point the telescopes in that area. And sometimes you just get these localization regions that are really, really big. And you're like, yeah, sure, but where in that region am I going to point my telescope in? So these are very challenging observations, but they're incredibly useful and informative. Now I'm going to take you back to this because I touched back on this, where I said that when we build a telescope, we cannot detect all of the electromagnetic spectrum. We cannot detect with one telescope both the gamma rays and the radio waves. We can't just do everything and get perfect precision. We focus on a specific region, and we built our telescope specifically with that region in mind. And in the same way that objects give off radiation at different frequencies of the electromagnetic spectrum, gravitational waves also come in these different flavors or these different frequencies, these different energies. So if I take you from your left, so this is the kind of regime that I've been talking about. So the ground-based experiments, what are these sensitive to? They're sensitive to things called supernovae. So this is what happens when stars die and they explode. They can give off gravitational waves. These pulsars, so these spinning neutron stars that can have some mountains that break spherical symmetry. And more relevantly, because these are the ones that we've observed so far, is these compact binary in spirals. So these merging neutron stars or merging black holes. But if we want to go to higher masses, so my favorite supermassive black holes, higher mass systems give off gravitational waves at lower frequencies. And but to detect these lower frequencies, you need longer and longer arms. Now, unfortunately, the planet that we live in has a very limited dimension. We can't just change it because we want to observe these gravitational waves, so we want to go up in space. These space observatories have the luxury of all the space that you want, and you can build these arms really, really long. And I'll show you a specific example in the next slide. And then towards even lower frequencies is when we become sensitive to higher masses of these black holes, but also to exotic, early, not necessarily exotic, but these early universe physics. So what is going on in the early stages of the universe's history? So what about these space-based observatories? Are we actually going to do this? And the answer is yes. So the European Space Agency has formally adopted what we call LISA. LISA is not a member of the Institute of Astronomy. Well, she is, but she works on different things. But LISA here means Laser Interferometer Space Antenna. And what this is it's 3 spacecraft that will be sent orbiting around the sun and trailing the Earth, and they will form a triangle. And by shooting lasers in these 2.5 million kilometer long distances, they can measure how this triangle is deforming, so how it's stretching and squeezing. And this is can be directly then tied back to gravitational waves that are passing through and deforming the space around it. And this is really an incredible mission. Whenever I talk to any engineers that work on this mission, or I try to understand it myself, I'm honestly in awe at how they managed to do this, because you need to get these like free floating gold cubes that are not touching anything, so that they're just sensitive to gravity. And it's really an amazing feat of engineering. But us astronomers are really excited for the results that will come from this in around mid-2030s, hopefully, because we can detect these individual mergers of these supermassive black holes now. And I told you that we're going to come back to pulsars. And this work, so pulsars were discovered by Professor Dame Jocelyn Bell Burnell when she was a PhD student, not quite like me, because she wasn't at the Institute of Astronomy, but she was at the Cavendish Laboratory. And just up the road from the Institute of Astronomy, there is a radio telescope observatory where Jocelyn Bell Burnell had her telescopes, and she was doing her observations as a graduate student. And at one point, she saw these kind of regular blips at regular intervals. And I think there was a joke, something where she wrote "little green men?" ? And it was a joke that she would write this if there's something that they don't understand, right? But it turns out that it wasn't aliens trying to communicate with us, but it was these really regularly spinning neutron stars that were giving off these like jets of electromagnetic radiation. This discovery of pulsars did go on to win the Nobel Prize, unfortunately, not Jocelyn Bell Burnell. But these pulsars are very, very useful because they act as cosmic clocks, because their rotation is just incredibly accurate and regular. So what we do to measure gravitational waves at very, very low frequencies is we build an array of these pulsars, and we call it a pulsar timing array. So we look out into our galaxy using radio telescopes, and we find these regular pulses from pulsars. And we can measure them across time, and we understand what the duration of their rotation is. Then if you measure a pulsar that is slowing down or speeding up, you keep track of that. And then you go and measure the slowing down and speeding up of another pulsar. You see how those two are correlated. And if they are correlated or related to each other in a specific way, which we call the Hellings and Downs curve, but that's not super important, then you've detected a gravitational wave background. What's this gravitational wave background? Well, it's a background of a lot of different gravitational wave sources that are kind of adding up together. They're interfering with each other, and they're creating this like hum in our galaxy. So rather than sounding more like a burp, now this sounds like a And we haven't yet detected it officially, but we found very strong evidence in favor of the presence of this gravitational wave background using these exact pulsar timing arrays. And we think that the dominant source that is sourcing this background is a population of these supermassive black hole binaries on the very, very high mass end that then come together and generate this hum in the background. And I'm not going to go into any details here, but what will we learn from these gravitational waves? Well, we're already learning a lot about the population of stellar mass black holes in our universe. And for example, once we get information from LISA and also from pulsar timing arrays, we can understand something that I'm actually trying to model theoretically in my PhD, which is how do the black holes actually find their way towards each other, and different mechanisms that bring the black holes together will imprint the different signatures on the gravitational waves. So there's loads of things that I haven't touched upon about what we can learn about these gravitational waves, but we're all very, very, very excited about the upcoming LISA mission and more data from pulsar timing arrays, and also as we're getting more and more data from the already existing ground-based observatories. And hopefully now you understand how we can listen to the universe and use a different sense to look at our universe. So thank you very much.
Wonderful. Do we have any questions for Stephanie? Yes.
Thanks for your interesting lecture. And I heard about that LIGO has detected many stellar mass black holes, right? And future LISA will observe large mass black hole systems. And combining this mass, the distribution and detection principle from this, the diagram that has mentioned before, I catch three pictures.
This one or?
Yes, three pictures. Yes, this and before two. Yes, and could LISA observation help solve the black hole's mass gap mystery that LIGO has found?
So LISA will be sensitive to different masses. So it won't be looking into the masses that LIGO is observing. Probably not directly, but what LISA will do is which will help us get a more complete understanding of the population of these black holes. So I've mentioned the stellar mass black holes, right? And I mentioned the supermassive black holes. But we don't know actually if there is intermediate mass black holes. So some black holes which are around maybe 10,000 times the mass of our sun. With LISA, we might be able to start to understand that question a little bit better. But yeah, so all these individual kind of observatories have their specific regimes of frequency and mass where they'll be sensitive, and LISA won't be sensitive to what LIGO is. So we might need future ground-based observatories for that, and there are plans for that to help us understand that problem.
So maybe more research will be done, will be due in the future.
Yes, definitely. Research is always ongoing, and you have these two main pillars, right, that are going on. So you've got the theoretical side, which is the side that I stand on, and you've got the observation side. So on the theoretical side, people are trying to explain the observations that we already have, right, trying to understand the physics, what could lead to this population that we're observing, and also trying to make predictions for the future observations. That's where I come in, trying to make predictions for LISA. And then you've got the observers that are actually taking the data, trying to clean up the data, understanding the data, giving it to the theorists, being like, does this match your models? Can you explain what we're seeing over here? And it's a constant dialogue between these two big pillars in astronomy, where this is how research goes forward.
It's very brilliant for you to do such a complex form. Very talented.
Thank you. Thank you very much.
Anyone else? Yes, please.
That was a brilliant talk.
Thank you.
How do you avoid the problem that presumably in the whole universe there are loads of events all happening? How do you avoid the problem that what you're detecting is the superimposition of
Yeah.
lots of different events?
Yeah, so I'm not an expert in the observations of these gravitational waves, but from what I've heard, LIGO is not that big of a problem. So I think the events that LIGO detects, they stand up above the noise quite well. But for LISA, that is going to be a big problem, because LISA is going to just hear so many different things. And it's called the LISA global fit, where essentially you can't just fit what you're seeing, for example, a supermassive black hole merger, but you have to fit all the other components at the same time to recover that signal. And that is a big challenge of data analysis, rather than the theoretical astrophysics that goes behind it. And I think that the UK is very much one of the leaders in driving that, that effort towards getting this LISA global fit. But yeah, that's a great question.
Okay, a couple more at the back.
How fast do the gravitational waves travel? Is that speed of light?
Speed of light.
And do you get like redshift? Do you get Doppler
Yeah.
shift from the expansion of the universe?
Exactly. Yeah. So because of that Doppler shift, you get lower. They're shifted towards lower energies. Yeah. And just to add on to that, so when I said they travel at the speed of light, that's the prediction from general relativity. So if you make an observation and you try and measure the speed of the gravitational waves and you see a deviation from the speed of light, then that might be a clue that maybe general relativity is not the full picture and we should be looking at different modified theories of gravity, which is what we're looking at. But so far, as it stands from all the tests that we've done, not just using gravitational waves, but everything else, general relativity stands true. So every prediction of general relativity has been proven to be correct so far.
I think I read something like that. Was there a correlation between light waves and gravitational waves for the same event, and that there was a slight difference in the arrival time?
I'm not so sure. Well, it might be, well, if we're talking about this one, for example, it might just be because you're probing different times at the evolution of the system, right? So the gravitational waves will happen when the two neutron stars in this case merge with each other. And then you can see along the axis there that after a specific number of hours is when the system starts giving off these different signals of the electromagnetic waves. So that might be the change in the arrival time, but not because of the speed of the electromagnetic waves, but just because you're looking at different evolution points in the system.
Okay, yes, please.
Great. I don't understand why LISA isn't a full-time pyramid to cope with all the different directions of the wave.
Again, I'm not an expert in the design of these gravitational wave observables, but so gravitational waves can create either like so the patterns are like a plus or a cross. So essentially, you need these two directions to see the polarizations. Yeah, I think that. Pretty sure that having this triangle is enough to detect these kind of and measure the gravitational waves. But yeah.
I guess also doing 4 rather than 3 is 33% more expensive.
Yes, a lot more expensive. Yeah.
Yes.
Is there a limit to how far you can detect the gravitational waves? Presumably, as they spread, they dissipate, and does that mean they over time get weaker as well?
Yeah.
Limit to how far we can hear them?
Yeah, so if I'm not mistaken, Lisa will be able to see out to redshift 20. So now I'm not quite sure how to make the change between redshift and age of the universe on the top of my head, but when we say...
I think redshift 20 is about, it's really young. It's like 50 to 100 million years old.
Yeah. Yeah, so essentially when we call redshift, it's because light get redshift, so it loses energy as it comes to us. So we use that as kind of a measure of the point of the universe. So redshift 20 is really, really young. And if we do actually observe gravitational waves coming from supermassive black holes coming out from these really, really high redshifts, that is a big, big question to answer, because we don't know where these supermassive black holes would have come from. Because there is a point where the first stars started to appear in the universe. And if you see gravitational waves from black hole mergers coming from before the first stars, then you might be having these black holes there before the stars, which is a theory called primordial black holes, which is really interesting and really intriguing, and is the kind of physics that we'll be able to do with LISA.
Okay, and last but not least.
Why is it that all the cubes in the thing are gold?
There must be a specific reason for this in the design of the observatory, but
Just makes them look nicer.
just makes it more expensive. No, I'm sure there's a reason, but I don't have the answer for you right now, unfortunately. Sorry.
Wonderful. Okay, well, thank you so much, Stephanie, for that wonderful talk.
Thank you.